What if I told you that the empty space around us is anything but empty? That it's far from being a benign void, but rather a simmering sea of potential, brimming with untapped energy? This isn't a pitch for science fiction. This is an exploration of what we call the quantum vacuum, a concept that dances on the delicate line between the tangible and the abstract. The idea of a vacuum, a space devoid of matter, dates back centuries. Aristotle couldn't fathom the existence of a true vacuum. He believed nature abhors an empty void. But the scientific revolutions of the 17th century introduced us to possibilities far more profound. By removing air and matter, early experiments allowed us to glimpse the idea of emptiness. Yet, even those historical scientists couldn't have imagined how rich and restless such a vacuum could truly be. The quantum vacuum, as it's understood today, doesn't align with what your everyday intuition would suggest. Most people imagine it as total emptiness, mere stillness. But in the quantum mechanical framework, it's a teeming, restless state where unobservable interactions govern its behavior. Here's the core idea. Even if you remove all particles and energy from a region of space, you won't reach absolute nothingness. The quantum fields that permeate our universe, they still whisper. To unpack what's really going on, we need to talk about quantum fields. Unlike in classical physics, where a field might describe a physical quantity like a magnetic field, quantum fields extend infinitely across all of space. Each fundamental particle, say an electron or photon, corresponds to a quantum field. These fields are present everywhere, even in the spaces you'd mentally label as vacant. In the vacuum state, all these fields are in their lowest energy configuration. But lowest possible energy doesn't mean zero action. Instead, it introduces random, restless fluctuations. This brings us to one of the most remarkable concepts: vacuum fluctuations. Even at zero-point energy, or the lowest possible energy state according to quantum laws, temporary particles and antiparticles flicker into and out of existence. These are virtual particles, short-lived and undetectable under normal circumstances. They annihilate one another almost instantaneously, leaving behind only the ghostly hints of their presence in phenomena like the Casimir effect. Now, if you're unfamiliar with the Casimir effect, oh, it's a marvel. This phenomenon occurs when two metal plates are positioned incredibly close in a vacuum. As they near each other, the quantum vacuum surrounding them creates a tiny but measurable force that pushes them together. Why? Because the distance between the plates restricts the wavelengths of vacuum fluctuations that can exist between them. Outside the plates, there's a broader spectrum of these fluctuations, creating an imbalance of pressure. Isn't that amazing? Even absence becomes active. Let's pause for a moment and appreciate how this changes our understanding of energy. Traditionally, energy is tied to tangible objects, spinning gears, moving masses, burning fuels. But with the quantum vacuum, energy becomes an inherent property of space itself. It's an ocean of possibility stretching across the smallest scales imaginable. Now, you may wonder, could this energy ever be tapped to power devices, or even civilizations? Here, we cross from present understanding into speculative territory. Theoretically, if one could exploit vacuum energy, the potential might be nearly limitless. But before we start imagining spaceships fueled by null-point energy, remember that modern physics doesn't yet let us access this energy reservoir efficiently, or even at all. Think of vacuum energy more like an exotic component of our universe's scaffolding, an enigmatic feature rather than an open resource. Instead, vacuum energy drives fundamental aspects of our universe. Take, for instance, the cosmological constant. This constant, introduced initially by Einstein into his equations of general relativity, is a small but persistent energy density spread across the universe. It's now associated with the vacuum energy landscape. Intriguingly, the cosmological constant is what fuels our universe's accelerating expansion, a fact verified by astronomers observing how distant galaxies speed away from us. But here lies a jaw-dropping conundrum. Using quantum field theory, the framework that underpins the behavior of subatomic particles, you can calculate the expected vacuum energy density. The result? A value so astronomically high that it's 120 magnitudes larger than the measured cosmological constant. Let me emphasize, this discrepancy doesn't just break predictive models, it completely demolishes them. Why is the observed value so small compared to theory? This remains one of greatest unsolved mysteries in fundamental physics. Could there ever be an explanation, or does this contradiction hint towards entirely new physics? Some theories attempt to reconcile this. Ideas range from anthropic principles, that we live in a universe where conditions for life are possible precisely because of such fine-tuning, to grand unifications of quantum field theory and gravity, but none are satisfactory. Yet. Jumping forward, the quantum vacuum has more surprises. It's not just theoretical, it manifests physical consequences. Hawking radiation, for instance, only makes sense by incorporating vacuum fluctuations near the event horizon of black holes. These fluctuations equip certain photons with enough energy to escape, a breathtaking realization that black holes aren't absolute, but gradually evaporate due to quantum mechanical effects. Another fascinating chapter: quantum foam. It suggests that at unimaginably small scales, the so-called Planck length, space-time isn't smooth, but froths with energy akin to boiling bubbles. This quantum foam isn't visible at macroscopic levels, but fundamentally challenges how we interpret geometry, time, and causality. At this boundary where space is thought to disintegrate into uncertainty, different proposals like string theory and loop quantum gravity step in, trying to forge new paths toward the elusive theory of everything. Here, vacuum energy isn't merely a peripheral idea. It is central, a piece of the puzzle about how space-time emerges in the first place. So, what should we take away from all of this? The quantum vacuum reminds us that the universe operates beyond our conventional understanding of emptiness and stillness. It is fertile, dynamic, mysterious, and essential to the very fabric of reality. Yet, it also presents us an immense challenge, because as advanced as our theoretical apparatus may be, the very existence and nature of the quantum vacuum suggests planes of reality yet to be uncovered. Now let me pose a final question to you, the physicists and theorists watching. If vacuum energy is such a critical but poorly understood source of untapped synergy between quantum and macrocosmic physics, what breakthroughs in defining it might arise first? Could experimental techniques, extensions of QFT, or something else altogether unveil it more directly? Share your insights in the comments below. I'd love to hear your thoughts on how we might one day unveil the full potential and truth of the engine of our reality, the quantum vacuum.